Now that we've looked at motion and forces, we can tie them together in a concept known as work, and it's a different meaning to what you might sort of see in everyday usage. So in physics it has a very specific definition, and that definition is that work is done when a force is applied to an object and causes it to move. And when we talk about the movement that we're dealing with here, we're interested in the displacement in particular. So we can calculate work by considering the force and the displacement. And I'll have an equation that we'll note here. But first of all, let's jot that down by considering the force and the displacement. So notice that we're talking about vector quantities here. So we need to be very specific about the fact that we're going to deal with displacement in the direction of the force. So we're only dealing with linear motion. There is an additional aspect to that I'll mention as we go through here, but we're just looking at the displacement in the direction of the force. So that basically means if we have, say, a box that's sitting on the ground and we apply a force to it in order to move that box, and at some later point in time the box is now moved to a new position over here somewhere, then the displacement of a box, let's say we use that front edge, that would be the displacement of the box in the direction that the force has been applied. So the work that would be done in that case is just given by the product of the force and the displacement. So force multiplied by displacement gives us the amount of work that's done. Just to mention it here, we're not going to actually need to worry about it, but just as a brief side note, so don't bother writing this down, if the force was at an angle, then what we'd be interested in is the direction of the force. So if that was our force there, we'd be interested in the direction of the force that causes the movement. So in this case it would be horizontal, and so we could so we'd be looking at the horizontal component, so that would be F cos theta, and then we'd multiply that by the displacement, which is usually expressed as Fs cos theta. And in vector notation, if you look at the way that it's covered in mathematics, you'll notice that that's the cross product of the two vectors. But just as a side note there, so you can tie that in to make a bit more sense of what's going on here if the force is not in the same direction. As I mentioned though, we're always going to be dealing with the force being in the same direction as the displacement, so no need to worry about that cos theta term. You only need to worry about this equation here that's in the data booklet, or the formula booklet. Note here too though, if there is no displacement, there's no work done. And an example of that is a situation where you apply a force, but you don't actually move the object that you're applying the force to. And so an example of that would be pushing on a wall. You can apply a force to the wall, but given that the wall doesn't actually move, then you're not actually doing any work on it. Even though you're expending energy, your muscles are doing something, we would say that no work has been done in that case. Now the units of work that we measure work in are joules, so spelled Joules, named after a scientist, and the symbol that we use is a capital J. Now 1 joule, you can think of it as being the amount of work that's done when 1 Newton moves an object by 1 meter. So if you were to substitute in a force of 1 meter, force of 1 Newton, a displacement of 1 meter, then the work that would be done there is 1 joule. That's kind of like the equivalent of lifting, say, 100 milliliters of water by 1 meter. So just to put it into context, the size of 1 joule. You'll also note that 1 joule, if we have work in joules, that's going to be equal to 1 Newton meter. So the units of joules are the same as the units of Newton meters, and the units of newtons would be kilogram meters per second squared, which we can get from Newton's second law, and so we can see that 1 joule in SI units is 1 kilogram meter squared per second squared. So given that newtons are kilogram meters per second, and then we've got to multiply that by meters again. So there's the SI unit equivalent of the joule. Now, when work is done on an object, that means that we've got sort of different perspectives here. When work is done on the object, we can talk about what the work is that's been done, or we can talk about this other property that we can associate with work, and we can identify that the object has gained energy. So another fairly simple equation here is basically that if you do work on an object, then it's going to cause the object to gain energy, so there'll be a change in energy for the object. Now we'll come back to that one because we need to look at this idea of energy in a bit more detail in a few different contexts in order to make sense of this this idea of work and energy being equal. To think about what energy is, though, it's sort of a little bit of a circular definition. Energy is basically the ability to do work. And so basically any time that something where you do do work on something and it gains energy, it allows that object to now do some work itself because it's gained energy. And there are different forms that we're going to discuss here briefly, and then we'll come back and look at a couple of them in more detail. We'll also look at some of these forms in more detail in class, because these are sort of fairly overarching terms, and we can sort of break them down into more specific terms. So the first generic type is kinetic energy, and you can think of that as being the energy of motion. So anything that's moving would have kinetic energy. As I said, there are some subcategories there that we'll have a look at. The second is potential energy. And you can think of potential energy as energy stored in an object. And again, we'll come back and look at those types of potential energy in a bit more detail. Given that work and energy are equivalent, that we can talk about if doing work on something means that it gains energy, then energy is also measured in joules. So work and energy are basically just sort of different perspectives of the same thing. And the last statement that we'll make in this video is that energy, and so when work is being done, we're basically transferring energy. So energy can be transferred between objects. So if we take one object and cause it to apply force to another one, we can have that energy being transferred. So it's being transferred from one object to another. So an example of that might be something like kicking a ball. So the movement of the foot, or the kinetic energy of the foot, gets transferred to kinetic energy of the ball. Or it can be transformed. So notice a slight difference in these two terms. Transferred is between objects. Transformed is within an object. So when we're saying that the forms of energy that are present are still the same, they're just being transferred from one within the object itself. So in the first example, with the transfer of energy, it was all kinetic energy the whole way through, so kinetic energy of the foot through to kinetic energy of the ball. When we're transforming, we're taking one form of energy, converting it to a different form of energy within the one object. So an example there might say be a bungee jumper. So when they are at the top of their jump, they have potential energy. There's energy that's stored due to their position in a gravitational field. And as they fall, that potential energy is converted to kinetic energy. However, regardless of whether energy is transferred or transformed, in all of those energy conversions, we are going to see, conversions, that the amount of energy we start off with will be the same as the amount of energy that we end up with. Now this is known as the law of conservation of energy. So in all energy conversions, the law of conservation of energy applies. So that's an important concept to understand, and I'll explain what that is in just a little bit more detail. So two ways to think of it. The first is that, as we've just sort of identified, energy cannot be created or destroyed. So we can't have energy being created out of nothing, and we can't have it being destroyed into nothing. And so as a result, all we can do with energy is transfer it or transform it. So there's the first way to think of the law of conservation of energy. The second way, so this will come back again when we look at a few different scenarios in a few videos' time, the total energy in a system before a particular event will be the same as it is after. So if we think about the situation of, say, kicking a ball, the total energy as the foot is swinging down to kick the ball will be equal to the total energy after the ball has been kicked. And in that case, the system that we're really talking about is just the leg and the ball. So there are other aspects outside of that that we're not really interested in. So it's only about the event itself and the system that's involved in that event. So there's a brief overview of work and energy. We'll come back and look at some more aspects of this in the next video, in particular relating to graphs and the rate at which energy is used.